Module 15G, we want to start talking about your collision reaction profiles, activation energy, understanding how this concept of activation energy, how it relates to variation of reaction rates with temperature. I need you to keep in mind your collision model as we go through this. Even though we're not actively talking about it, you need to be thinking about it with those transition states, your reaction coordinates, if the process is endothermic or exothermic, and also understanding how catalysts work. So transition state theory. This is a reaction energy profile or a potential energy diagram, basically showing you at what point in the reaction coordinate you are and what is the potential energy of the reaction at that point. Both examples shown here are exothermic reactions. How do I know that? It's because the potential energy of the reactant is higher than the potential energy of the product. In an exothermic reaction, delta H here, the difference here is delta H, is a negative value. It is exothermic. Activation energy, E sub A, is the energy required to hit the transition state for the reaction to actually occur. So it's the combined kinetic energy that the colliding particles must have for the reaction to be able to go forward. We can see it again here with the particles, looking at an example we've already looked at, the NO2Cl reacting with a Cl molecule to produce NO2 and Cl. The reactants come together. They have enough energy to hit that activation energy, to overcome that activation energy, to go through their activated complex. This is their transition state. And once complete, they produce their products, and we see the potential energy of their product at a lower point. Therefore, this is an exothermic reaction. You need to be able to understand these. You need to be able to draw these reaction energy profiles. So here's one drawn, not great, but you get the point. An endothermic process, you've got your reactants. Your products are at a higher potential energy. Endothermic means that I put energy into that system. The delta H of reaction here would be a positive value. This is your change in energy, and its delta H reaction is positive because it's an endothermic process. Your activation energy goes from the reactants to the top of your transition state. How much energy did it take to reach there? Again, the reaction coordinate can also be called your progress of the reaction. And we can see, again, for exothermic, same type of process, your reactants to products, except the change in energy here, the delta H would be a negative value because it's exothermic. Again, you can call this progress of reaction if you feel like it. If it makes more sense in your brain, I don't care. But it's a potential energy diagram. And your transition state. So if I gave you a reaction and said these particles are coming together, it's an endo or exothermic process, or I told you this process has a delta H that's positive or negative, or I said it's hot to touch, cold to touch, etc., you should be able to draw me a diagram like this with the particles themselves showing the orientations in space. How do catalysts come into play? Catalysis. How does a catalyst increase the rate of reaction? Activation energy, E sub A. The higher the activation energy, the slower the reaction is going to occur because it takes more energy to reach the activation energy, right? It takes more energy to overcome the activation energy required to reach the transition state. A catalyst speeds up a reaction by finding an alternate route or path with a lower activation energy. Two important principles. Again, activation energy, activation barrier. Again, remember, the higher the activation energy, the slower the reaction. The catalyst is going to speed this up by finding an alternative pathway. It's like I have multiple ways to get to work. I can pick the one that leaves me with the least bit of stress and annoyance and traffic, etc. That is lowering my activation energy for the day. Catalysts increase the rate of reaction, but they are not consumed in a reaction. They are not considered a reactant. They create a new pathway with a lower activation energy. Due to this new pathway, more collisions occur that have enough energy to successfully form products. Catalysts often activate or weaken one or more bonds in the reactants and or help to properly orient the reacting molecules, thus promoting the reaction to increase. So catalysts increase rate of reaction by lowering your activation energy. They do this again by finding a different pathway for the reaction to go. So as we see here, if we were looking at a catalyzed versus uncatalyzed path versus potential energy, you've got your reactants and they're starting at the exact same point. Products, same point. When I look at the uncatalyzed pathway, I see the energy required to reach the activation, overcome activation energy is here. This is a large difference. For my catalyst, it's a much smaller difference. The activation energy is smaller for the catalyzed reaction for uncatalyzed, because the catalyst found a different reaction pathway to follow. Lowering your activation energy requirement, which allows the reaction to be more successful. When the catalyst is present, the activation energy is less, the rate is then faster. More collisions are going to occur, the reaction is going to be more successful. You can have homogeneous and heterogeneous catalysts as well. Homogeneous are just catalysts that are in the same phase as the reactants. So, all liquid phase, all gas phase, whatever you're looking at. Or you can have heterogeneous. Heterogeneous is in a different phase from the reactants. So, for example, here we have catalyst. The catalyst is a solid phase, and the reactants and products would be in a gas or an aqueous phase. They don't have to be the same phase, but they are something that you will see in the reaction mechanism where they're in the elementary steps, they are involved in the reaction. But they are not part of the overall reaction because they are first consumed, then again regenerated before the reaction's over. So catalysts are used up in one step, but then reproduced or regenerated another step, which allows a very small amount of catalyst to go a long way in an overall reaction.